Okay, so if you'll take out your purple note-taking guides, we're going to talk about circles today. Now, some of these definitions we've already looked at, so you may already have some of these definitions, but let's talk about them. So the first one is for a circle. A circle is the set of all points in a plane that are equidistant from a given point. And that given point is called the center. So that pretty much defines both of them. The center is the point from which all points on a circle are equidistant. The center is also the midpoint of the diameter. A radius. A radius is a segment that connects the center to a point on the circle. Guys, shh, you may whisper, but I'm recording a lesson, okay? You may whisper. A radius is a segment that connects the center to a point on the circle. A chord is a segment whose endpoints lie on the circle. Now, a diameter is a special chord. It's the longest chord. It's a chord that passes through the center of the circle. A secant is a line that intersects a line, a ray, or a segment that intersects the circle in 2 points. And a tangent is a line that intersects the circle in 1 point. And you may think of that as just touching the circle in 1 point. Okay, so let's look at this. Tell whether the line, ray, or segment is best described as a radius, chord, diameter, sequent, or tangent to circle C. BC, so if we look at the segment BC, which is the segment here, it is a radius. C is the center and B is a point on the circle. Line EA, well, line EA is this line here, and it looks like it's passing through 2 points, so that would make it a secant. And ray DE, so from here this way is ray DE, and if we notice it touches the circle in 1 point, so it is a tangent. Okay, now this is somewhat of a review. The radius of A would be 2 units. Therefore, the diameter would be 4. The radius of B is 4 units. So the diameter would be 8. This one asks us to tell how many common tangents the circles have and to draw them. So I've already drawn them in. A common tangent means it is tangent to both circles, so it touches both circles in 1 point. So if we look at A, if you're looking in your book, you can see how I've drawn in the red tangents here, and there are 1, 2, 3 common tangents. If we look at this one, there are 2 common tangents, and this one just has the 1 common tangent. Okay, so you take a look at these and you try. How many lines are tangent to both of the circles? Well, number 3, there are no common tangents. Okay, on this one, you may see these 2 right off the bat. I can't draw them very well. But there are also 2 more that go through the center. So this one has 4 common tangents. Okay, in a plane, a line is tangent to a circle if and only if, and the abbreviation for if and only if is IFF, if and only if the line is perpendicular. And that is nice because there's a lot of math we can do with this. Perpendicular to the radius. So it is tangent only if it is perpendicular. Well, that's helpful because that can lead us to problems like this. Well, if it is tangent, then it is perpendicular. And if it's perpendicular, we've created a right triangle. So what can we do with a right triangle? We can use the Pythagorean theorem. So in this problem, it's asking it, is ST a tangent? Well, if it is, this better be perpendicular. Therefore, the Pythagorean theorem better work. Does 10 squared plus 24 squared equal 26 squared? Yes, it does. So it is a right triangle. And RS is perpendicular to ST. So ST is the radius. Is the tangent. All right, now hopefully you notice that this is just the multiple of one of our Pythagorean triples that I asked you to know. This is just the multiple of 5, 12, 13. See, 2 times 5, 2 times 12, 2 times 13. Easy to spot. Okay, so in this one, let's check to see if these are tangents. So if it's tangent, it better make a right triangle, and Pythagorean theorem ought to work. Well, if this radius is 5, this one is also 5, so the hypotenuse of this one is 13. So we would say 5 squared plus 12 squared. Well, yes, it does. That's our famous Pythagorean triple. So yes, it is tangent. Now on this one, we would say 12 squared plus 16 squared should equal, what would this be? 12 plus 7, 19 squared. Well, if I look at this, this is a multiple of the 3, 4, 5. This is 3 times 4, 4 times 4, so this should be 5 times 4. These are not equal. This should be 20. So this one is no. ST is not tangent to the circle because of the converse of the Pythagorean theorem. Okay, now how can we use it to find missing sides? If it tells us it is tangent at this point, then we know that this forms a right triangle. So we could say that leg squared plus leg squared equals hypotenuse squared. So r squared plus 77 squared would equal the hypotenuse, which is 49 plus r squared. So when we do 49, r plus 49 squared, we need to think of it as r plus 49 times r plus 49. So when we distribute through here, we're going to get an r squared, we're going to get a plus 49r, and another plus 49r. So we did first terms, outside terms, inside terms, and we do last terms. 49 times 49 is 2,101. So this gives me r squared plus 98r plus 2,401 is equal to 77 squared, which is 5,929. So if we look at this, the r squareds are going to cancel when I subtract those. And I'm left with 98 is equal to 3,528. So r is 36. So we've used what we know about a tangent being perpendicular to the radius to solve for missing sides. Okay, now on this one, we pretty much proved this when we were doing constructions, but if we took our compass and put the point here and then marked this distance, if we came over here, it would mark exactly the same for the tangent. So we know that those two tangents from one exterior point are congruent. And we can use that to solve. So here it says we have circle C, and it says we have Q tangent and QS is a tangent. So since they're tangent from one external point, we know that these two tangents must be congruent. So 32 must equal 3x plus 5. Subtract 5, divide by 3, we get x equals 9. We can use that same thing here. So here we would just say x squared, 49, so x is 7. All right, now the next section talks about arcs and central angles. So just a refresher, a central angle is an angle whose vertex is at the center of a circle. Now we have some more definitions here. A semicircle is just half the circle, and its measure is equal to 180 degrees. An arc is just an unbroken part of the circle, and we define them as minor arcs and major arcs. Minor arcs are less than 180 degrees, and we'll name those with only 2 letters. Major arcs are more than 180 degrees, and they are named with 3 letters. Now, congruent circles. We can prove congruent circles if we have circles that have congruent radii that are the same. We can prove congruent arcs, which have the same measure, by showing circles that have congruent radii and congruent central angles. So we have to have those 2 things to prove congruent arcs. If we look at this, the measure of a minor arc is equal to the measure of the central angle. So if this central angle is 50, the measure of that arc is 50. So the measure of arc AB is 50. Now, the measure of the angles of an entire circle are 360 degrees. So to get the major arc here, ADC, what we're going to do is take that 360 and subtract from that the minor arc. So if we do 360 minus that minor arc that we don't want, that will leave us with the part we do want. That'll leave us with the major arc. So 360 minus the minor arc leaves us the major. And that's where we get the 310. Now, the measure of any semicircle is 180 degrees. So anytime we have the diameter in there, that tells us we have a semicircle and it's 100 degrees. So here we have the measure of DE. Well, here's my angle. So DE is going to be a minor arc. And it's equal to the measure of that central angle I just showed you, ECD. And that angle is 117 degrees. Now, DFE is this big arc right here. So this major arc. So we're going to do 360 minus that minor. And that tells us that this angle is 243 degrees. Now DF is a diameter, so arc DEF is a semicircle. Ooh. There we go. And its measure is 180 degrees. Now in this example, it asks us to find RTS. So the order of the letters matters. It tells us to go this way. And RTS would have a measure of 360 minus the 45, so it would be 315 degrees. Now, this says that if an arc can be formed by the sum of two others, arc ABC can be formed by the sum of AB plus BC. And it gives us that full arc. We're going to skip this example. Now, this is asking us to prove if the arcs are congruent. So the two things I told you needed are congruent radii and congruent angle. So here we have congruent central angles, and it's the same circle, so obviously we have the same radii. So are those congruent? Yes. Here we have the same central angle, but we have two different radii, so no. Here we have the same central angle, and we have congruent radii, so yes. Shh. All right, this one, is PQ congruent to arc SR? So are these two arcs congruent? Well, they are. And they are congruent because we have congruent central angle and the same radii. All right, your homework is the problems that are listed on the calendar online. It's 2 sections out of your taking guide and some problems out of each. So if you'll pull up the calendar online, you'll see your homework.